Hi, and welcome to the practical exercise of scaling, resizing, interpolations, and cropping. So let's take a look at our code. Alright, so now let's start doing the practical exercise of our last chapter, which is code number 5, scaling, resizing, interpolations, and cropping. So click on this IPython notebook, and let's bring up our code, okay? So firstly, I have some notes here which describes how to use the resizing function, what the desize argument is, which we will see shortly, alright, and a list of interpolation methods here. But before we take a look at this, let's just actually run the code here. So I'm going to read a bit through the code and before I run it. So now, firstly, we're loading our test image here, which is a picture of Oxford that I took last year being 2019. And what we're going to do, we're going to use the resize function here. So the resize function takes a few arguments here. We take our image, we put none here. Now I'm going to describe to you what none is here. None is the desize argument here, which is the output image size. Now by putting none or 0, what it does, it actually uses the dimensions of what we scale here as. Otherwise, you can actually scale an image and then put some dimensions here that you want it to be, which keeps it fixed. However, I don't use this terribly often. Just kind of use the scaling to actually get the image size that I want. So now you're seeing fx and fy as our third and fourth arguments, and you're seeing I'm using 0.75 here. What this is saying is that I'm going to scale the x-axis here. X-axis actually being this one, the horizontal axis, by 0.75% of the original size, which is 3/4 of the original size, same thing. And the y-axis, which is the vertical axis, or the height, I'm scaling to 75% of the original. And we don't specify an interpolation here as a fifth argument here. And that's because by default, we're going to use interlinear. That's the default resize argument or interpolation method. However, in a few other examples here, we're going to specify different interpolation methods here. Intercubic, internearest, and interarea. Now, if you remember correctly, intercubic is a lot slower than internearest, which is one of the fastest one. Interlinear is also quite fast as well. Interarea is pretty much in between, it's also quite fast, but they're not terribly different when you actually look at the outputs. However, I do see a big difference sometimes with using intercubic. So now let's run this code and take a look at our different scaling methods. So let's try this. So this is our 0.75 or 75% of our original image. We scaled it down or downscaled it here using linear interpolation as a default interpolation method. Now let's upscale this image to twice, which is why fx and fy are 2, and using cubic interpolation. And you can see it's actually pretty good. It doesn't look noticeably upscaled, although I mean I can tell it is, but it's not too bad. Now let's take a look at internearest, and internearest looks good. However, to me it seems a bit harsh and a bit jagged in some areas, whereas intercubic does look a bit smoother. You can look at them side by side. Hopefully the image quality of your video is good enough for you to detect the difference. However, as you can tell, look at this building here. You can see it's a bit jagged, especially coming down here where intercubic is a lot smoother and more natural looking. So that's a positive of intercubic. And now we can actually do skewing, which is when we specify our fy to be different to our fx, which we'll see in the code. This is actually what I wanted to teach you. We can change fx and fy to different values and get different types of scaling or resizing. However, you also can input dimensions here. Now these dimensions here, the outputs, is using the desize argument now, and you're ignoring these arguments here, which is why they're not in the arguments of this function here. By default, they're 1 to 1, and now we can just actually output the specific dimensions we want. So if you want to resize images to a specific size, you can actually use this here as a desize. And this is actually pretty cool. You can just basically change the ratios. So now this is actually resizing and not scaling, okay? So this is actually phrased wrongly, but that is okay. If you absorb this lesson, you would know where the terminology is used incorrectly. And I apologize for that. So now this is some experimental code I'll delete. And now let's take a look at image pyramiding now. So this is quite simple. Have our image here, our original image. PYR, which is pyramid down, makes the image smaller by half. So it's using fx as 0.5 and fy as 0.5. And py up is basically using fx and fy as 2. So we take the image, we make it smaller, and we create smaller here. Now we're feeding smaller back into our pyramid up, and we're creating a larger image. However, you'll see the quality isn't going to be good because what's happening here is that we've taken the original image here, we've scaled it down, so we already have lost some information in the image by scaling it down. and we're taking this lower information image and blowing it up back to the original size, because this is a half and then double again. So that's why we end up with this very blurry image here. So you can see it side by side how much worse quality it is. So that's what our image pyramids are done. Now, they're not really useful for resizing. They're more useful in object detection when you want to just get quickly resize images for different operations. So it's good that you've learned that. Now let's take a look at cropping. Now, cropping can appear a bit tricky. However, it's quite simple. So what we're doing here, let me step through the code. So we're just getting our input dimensions, image dimensions here, which is the height and width by using the shape arguments here. And what we're going to do, this is just getting the coordinates of, it is the coordinates of our cropped region. So what we're doing, imagine or remember, actually I have a diagram that I can illustrate this here. All right, so it's easier to explain what I described in the code in this diagram here. So let's put this side by side with the code so you can actually see what's happening. All right, so the area we want to crop, imagine this white canvas here is the entire region. So let me just make it tad, it's a bit hard to get the exact high as I want to do, but this is still readable, I'm guessing. So imagine we want to get this region here cropped out of the original image. So imagine this whole white canvas here is our image, and we want to crop the middle rectangular square of this image here. So what we're doing, we're going to move 0.25 down here, which is why I have 0.25 times the width and 0.25 times the height. That is our start row and start column here. Those are these points here. So just like drawing a rectangle, we have to get the top left vertice and then the bottom right vertice here, which is going to be 0.75 times the height and 0.7 times the width, which we get here. So end row, end column. So that's relatively straightforward. Don't think about it as being complicated. It's a bit much to look at, but it's not complicated, all right? So quite simply, when you want to crop an image, you use this indexing here. So this is a function of NumPy lists, or just Python lists, I should say. So you actually just get the start here, start row to the end row. We just want these columns here, or these, I should say, array list elements here, and these elements here. These are the elements we want to extract from our original list here. So that's actually it, all right? Now, what I'm going to do in the other code here, I'm just going to actually draw the area using the CV2 rectangle. And CV2 rectangle, by the way, is an in-place operation, which means that it actually draws a rectangle over the original image, which we don't want to do. So just use image.copy to create a copy of the image, and that copy will be the one that the rectangle function draws over. So hope I don't confuse you, but then now let's just run this code starting from the top. So this is our original image, nice and clean. This is the area we want to crop. This is the area that, remember this is 0, 0. So this is 0.25 down, 0.25 here, and then this is 0.75 down and 0.75 here. That's how we get the end and start columns and rows, so the end vertices. And this is our cropped area. So you can see this is exactly what we cropped out of it. You can actually put it back here just to kind of overlay it. Because it's a window, it's a bit tricky, and because of the rectangle width, it doesn't actually line up perfectly, but you can see it is exactly the region we wanted. So cropping is extremely important and extremely useful in computer vision. So it's a useful thing to know, and keep in mind that this code is actually quite simple. This is all the cropping function is. It's not a function, it's actually just the way we do it. So all of this code is just to illustrate this one line here. So that's it for this video. So now just to summarize what we've learned in this video. You've learned the two different methods to resize images in OpenCV. Just to reiterate, that is the FX/FY, or using the desize method to specify the actual dimensions of the output resized image. You've learned how to specify or change different interpolation methods. You've also used the pyramiding functions, which is CV2 pyramid up and pyramid down, as well as you've learned a very important tool, which is how to crop images. So now let's move on to arithmetic and bitwise operations. Thank you.